The field of artificial intelligence functions as a structured engineering discipline, organized into a rigorous technical hierarchy. At the highest level, AI involves the development of systems capable of performing tasks that typically require human intelligence, such as decision-making and environmental interaction. Machine learning is a subset that learns patterns from data without explicit programming. Deep learning specializes this using multi-layered artificial neural networks. Generative AI shifts focus to creating new data samples, while natural language processing bridges these techniques for human-language interactions. Engineers must first identify where a problem sits within this hierarchy to determine the appropriate tools and methodologies for the task. The selection of a model architecture depends on the structure and availability of the training data. Labeled data provides a predefined ground truth for the algorithm, while raw, untagged information requires the model to find its own internal logic. Based on this distinction, developers select a learning paradigm: supervised, unsupervised, or reinforcement-based. These data labels act as the primary constraints that determine how a machine is permitted to learn. In supervised learning, algorithms learn from labeled data. Unsupervised learning removes those labels, uncovering hidden structures within raw data. Semi-supervised learning uses small labeled sets to categorize large volumes of unlabeled data. Finally, reinforcement learning trains agents to make sequential decisions by receiving feedback in the form of rewards or penalties within a dynamic environment. These four paradigms provide the functional framework for nearly every task in modern machine learning. Supervised learning supports classification tasks. It also powers regression, predicting values like house prices. Unsupervised learning enables clustering, vital for customer segmentation. This approach also detects anomalies, identifying outliers in cybersecurity networks. Many advanced systems, like facial recognition, integrate multiple paradigms to reach their objectives. The nature of the task determines the learning paradigm used, which dictates how we measure performance. This process is managed through a 10-step lifecycle, from problem definition to model selection. Step 7 is model evaluation, where logic is validated against data it hasn't seen before. Engineers often start by looking at a model's accuracy, the proportion of correct predictions out of total attempts. However, accuracy can be deceptive. If a model correctly identifies 99% of transactions as safe, but misses the 1% that are fraudulent, the high accuracy score masks a total failure. True performance evaluation requires a confusion matrix to categorize the specific types of errors. A confusion matrix breaks down predictions against true labels to diagnose weaknesses. True positives and true negatives represent correct predictions. False positives are false alarms, while false negatives are missed detections. These values allow us to calculate two critical metrics: precision and recall. Precision measures true positives out of all positive predictions, showing how often a positive claim is correct. Recall measures true positives out of actual positive instances, capturing real-world cases. To balance the two, we use the F1 score, representing the harmonic mean of precision and recall. By analyzing these metrics, engineers decide whether to tune a model to avoid false alarms or to ensure no actual cases are missed. This journey moves from the overarching AI taxonomy, through data-driven paradigms, to the evaluation of performance through the specific quadrants of a confusion matrix. This evaluation leads directly to step 8 of the lifecycle, model tuning. This creates a cycle where metrics inform the next round of training. Only after these metrics meet the project's requirements does the model move to deployment and ongoing maintenance. This engineering pipeline ensures that every prediction is deconstructed, analyzed, and systematically improved through a measurable framework.